Chemical Kinetics Part 15, Temperature and Rate of Reaction. This is the second factor that can affect reaction rate. We've already looked at the physical state of matter, and in future videos we'll take a look at a catalyst. But in this video we're going to consider the temperature and how that affects reaction rate. And specifically we're going to look at the Arrhenius equation and how to calculate K, the rate constant, at different temperatures. So when we are considering temperature and reaction rate, the higher the temperature, the increasing frequency of collisions. And a higher temperature also causes an increase in the energy of collisions. And that can all be summed up with a larger K, or rate constant. So the number of molecules graphed out on the y-axis versus the kinetic energy on the x-axis for a low temperature sample of molecules versus a high temperature sample of molecules might look something like this. Notice that the distribution of the area under the curve for a lower temperature sample of molecules would be farther to the left on the kinetic energy axis. And the distribution, or the area under the curve, for higher temperature molecules would be farther to the right. Now if we said that this dashed line represented the activation energy, or the minimum energy needed for a reaction to occur, we can see from this diagram that the larger fraction of molecules, symbolized with a lowercase f, will occur when we have a higher temperature. In other words, the area under the high temperature curve is bigger than the area under the low temperature curve that's shaded in a little bit more darkly there. Now Arrhenius said that the fraction of molecules that reacts, in other words, the fraction of molecules that have a kinetic energy that's greater than or equal to the activation energy, can be described as F is equal to E to the negative EA over RT power, where EA is activation energy, R is the ideal gas constant represented in joules per mole Kelvin, and temperature is in kelvins. Let's take a look at the Arrhenius equation. So here we have a graph of K, the rate constant, versus temperature. And what you can see is that increasing temperature is going to cause an increase in the rate constant. In other words, as we go further on the x-axis to the right, the K value gets bigger. This is going to be angling upwards. For most reactions, increasing rate with increasing temperature is nonlinear. For most reactions, we'll have some kind of a curve there. So remember that the differential rate law says that the rate is equal to K for a zero order reaction. It's equal to K times the concentration A for a first order reaction, and it's equal to K times the concentration of A squared for a second order reaction. Now we're considering reactions here with a single reactant, chemical A, forming products. We can see that there are going to be three factors that affect K, the rate constant. Arrhenius said that K was equal to A, what he called a frequency factor, times F, the fraction of molecules that have sufficient energy for the reaction to occur. They have energy that's greater than or equal to activation energy. Remember that we said F was equal to E to the negative EA over RT power, where R is the ideal gas constant, 8.314 joules per mole Kelvin, and T is temperature in Kelvin. A is the frequency factor, and there are two components to that frequency factor. One is the frequency of collisions, and two is the probability of proper orientation. So frequency of collisions, the orientation of the particles when they collide, and the third factor that affects K is the fraction of molecules with the activation energy or greater amount of energy. So this is our first version of the Arrhenius equation. Doesn't seem very useful in that form, so let's take care of that. Here's that first version of the Arrhenius equation. Remember, this is what F is equal to. Now the factor A is not exactly constant because A does have a temperature dependence. Increasing the temperature increases the number of collisions, and remember, A is affected by the number of collisions, the value of A. However, the exponential effect of temperature on the factor F, notice that T is in the exponent here, so the exponential effect of temperature on F, in other words, the fraction of molecules that react, is much greater than the effect of temperature on A. So while A does fluctuate a little bit with temperature, F fluctuates a lot with temperature. So in comparison, we can treat A, the frequency factor, as a constant. A is temperature dependent, but not nearly as much as F. That's important. So let's go ahead and substitute this expression in for F. This equation becomes this equation, right? Instead of using F here, we use e to the negative EA over RT power, where R is equal to the ideal gas constant, expressed this way, and temperatures in kelvins. Now, take note that as activation energy gets bigger, so you get a bigger activation energy here, because this is a negative exponent, the K value is going to get smaller. Also notice that as the temperature gets bigger, it will make the value of the negative exponent smaller, and as a result, a bigger temperature would mean a bigger K value as well. So we can say that the Arrhenius equation looks like this, where A is the frequency factor treated as a constant, F is the fraction of molecules with the activation energy or greater, and energy equal to the activation energy or greater. We could express F this way, and we could substitute this in and make this equation into this. What we're going to do now is take a look at how the Arrhenius equation can look like this. Again, R is the ideal gas constant expressed like this, T is temperature in kelvins, and EA is the activation energy. And since we have joules in this expression for R, we have to have activation energy in joules. That's important when you do problems. Make sure that your units match up. Sometimes in a problem you'll be presented with activation energy in kilojoules, and you'll have to convert it to joules so that it matches the units in R. Well, let's see how we can get to this equation. That's our really useful form of the Arrhenius equation. Here we have the Arrhenius equation expressed that way. Notice that if rate constant K1 is known at any given temperature T1, in other words, if we know the value of K1 and T1, then the rate constant K2 can be calculated at any different known temperature T2. So if you know K1 and T1, and you want to speculate as to what the rate constant K2 would be at a different temperature T2, you can plug into this equation and find that. So let's show how we can derive that equation. Here's our first version of the Arrhenius equation. This is the expression for F, the fraction of molecules that have energy equal to activation energy or greater. We plug that in here. Remember that A depends on the frequency of collisions and the orientation of the molecules. It has two components to it. Since A does depend on frequency of collisions, it is somewhat temperature dependent, but not nearly as temperature dependent as this expression, since temperature is in the exponent here. So we treat A as if it is a constant, even though technically it's not exactly constant. That's important as we go through this derivation. Now, what we're going to do is take a natural log of the left-hand side and of the right-hand side. So a natural log of k is equal to a natural log of a, and then we get plus a natural log of e to the negative ea over rt. Natural log of k will just carry down here on the left-hand side. We'll carry down the natural log of a, but remember that the natural log of e to the x power is just equal to x. So this right-hand side solves out to be negative ea over rt. That means the right-hand side of the equation is the natural log of a minus ea over rt. Let's rearrange that and say that the natural log of k is negative ea, activation energy, over rt plus lna. Now we're going to come back and check a graph as to why we can do what we're doing here, why we would do this. But let's just say that we take the natural log of k in situation 1 and we make it equal to negative ea over r temperature in situation 1 plus the natural log of a. And then we do that again for situation 2. So the natural log of the rate constant k in situation 2 is equal to negative ea over r times the temperature of the chemical in situation 2 plus lna. Let's subtract this equation minus this equation. So the left-hand side, natural log of k1 minus natural log of k2, is equal to the right-hand side, this expression minus this expression. So let's rearrange this a little bit. What we can do here is say that the natural log of a is going to be the same because we said that we're going to treat a as constant. So we have natural log of a minus natural log of a. That means natural log of a becomes 0. Natural log of a minus itself becomes 0. So now we have negative ea over rt1 minus negative ea over rt2. So if we distribute that negative sign, a negative of a negative makes a positive. So we have positive ea over rt2 minus ea over rt1. Now we can say that the natural log of k1 minus the natural log of k2 is the same as the natural log of k1 divided by k2. And that's equal to, let's factor out ea over r, and over here we'll have 1 over t2, and over here we'll have 1 over t1. So it's on the right hand side negative, or rather ea over r multiplied by 1 over t2 minus 1 over t1. And this is our useful version of the Arrhenius equation. So let's just do a quick math review here. Remember that we said natural log of k1 minus natural log of k2 could be expressed as natural log of k1 divided by k2. Right? We took this equation on the left and made it look like that on the left. So remember, the natural log of e to the x is equal to x. And I like to use log base 10. They're a little bit easier to wrap your mind around. Log of 10 to the x is equal to x. So we could say log of 10 to the 5 is equal to 5. Log of 10 to the 3 is equal to 3. So 5 minus 3 would be 2. Log of 10 to the x minus log of 10 to the 3 should be log of 10 to the 2 then, because log of 10 to the 2 is 2. So notice that if we have log of 10 to the 5th minus log of 10 to the 3rd, we could say it's log of 10 to the 5 divided by 10 to the 3rd. And remember that when you have exponents with a common base, we can just say that the log is equal to the base with the top exponent minus the bottom exponent. 5 minus 3 is 2, and of course the log of 10 to the 2 is 2. So it's a property of natural logs or logs that you could rearrange this into this. And that's all that we did down at the bottom of this equation here. Now before we go on and wrap this up, I did want to take a look at, well, why did we do this here where we solved for this equation in situation 1 and situation 2 and then subtracted those two? Let's consider that when we do this derivation and we get down to this part, this looks an awful lot like a slope-intercept form of a line equation, right? We can just factor out negative EA over R, and we'd say that the lnk would be the y-axis value, the inverse of temperature would be the x-axis value, the slope of the graph would be negative EA over R, and the natural log of A would be the y-intercept, or the B value. Well, that means that if we graph out natural log of K on the y-axis and the inverse of time on the x-axis, we're going to get a straight line graph, right? This is a slope-intercept form of a line equation. So the y-intercept would be the natural log of A. The slope would be negative EA over R. Now remember, the slope of any graph is the change in y divided by the change in x. So the change in y could be the natural log of K1 minus the natural log of K2. And the change in x could be the inverse of T1 minus the inverse of T2. So then delta y divided by delta x becomes ln K1 minus ln K2 divided by 1 over T1 minus 1 over T2. And we could rearrange that equation, right? That's all equal to the slope. We said that this is the slope. We can rearrange that equation and we'll get this expression. Well, that's the same thing that we got here. And hopefully that clears up why we did this subtracting of the equations. Now, you're probably never going to have to go and derive this equation on your own, but you should know that this equation allows you to take a known rate constant K1 at a known temperature T1 and solve for the rate constant K2 at some other temperature T2. And that's the useful form of the Arrhenius equation.